then let's move to Dr. Hussein. Dr. Hussein is working on a similar topic. He works on wearable and flexible electronics, sensors, and other microsystems. He uses contemporary micro and nano manufacturing techniques to embed these sensors wirelessly into structures for health monitoring purposes.
Yeah, thank you, Brown.
Go ahead.
I am Hussein Nesser. I am a postdoc at KAUST University working with Professor Gilles Lubino on ultrasensitive wireless strain sensor for structural health monitoring. So all structure in all domain, including oil and gas, civil engineering, aerospace, and all the other domain subjected to internal and external factor that can may cause a damage or degradation or sometimes catastrophic problem. So to avoid this problem, we need to monitor the structure. How we can monitor this is by this green point, so by monitoring system. And this monitoring system also can be interesting or useful for testing lab application, like testing the durability of the material by testing, making strain test analysis or fatigue test. So in the literature or in the market, there is a different type of traditional nano-destructive testing technique, such as ultrasonic, thermal stress field like infrared camera, X-ray. And the best two method to monitor structure is the fiber Bragg sensor and the strain sensor. Why they are the best? Because they can monitor in the real time the structure by detecting the strain. But this two method contain cable and wire. So sensor with cable is not adaptive for embedded monitoring system, and also for some advanced industrial and engineering application, like everything with rotation. And also the cable affects the measurement accuracy, especially for the in lab test. So our objective is to fabricate or to create a new generation of sensors that can be communicate with data processing wirelessly, that can be embedded without any problem in any type of structure. So our objective is to create a sensor with free wire and free battery. How? We can do that by inductive coupling. It's it's like RFID or credit card, wireless credit card. So the idea is to communicate between two coils or transfer the data and energy between two coils by inductive coupling. The first coil is the read-out coil that connected to a portable reader that can be a computer or a laptop, and the second coil is a part of LRC tag. This LRC tag is our strain sensor, so it contains the inductive or the coil. The second element or the second component is the inductive capacitance, and the third component is the cracked resistance, the cracked electrode. Why? Because this cracked electrode will be sensitive to strain. So when we're applying external strain, a variation of resistance appear. And this variation of resistance we can detect it by following the resonance frequency or the quality factor of the resonance frequency of this oscillating circuit. We see here how the quality factor is dependent of the resistance. So when we change the resistance, when the resistance is changed, we can, by following the resonance frequency, we can detect this resonance, this variation of resistance. So we can follow the external strain. So our wireless strain sensor is fabricated by a durable material and very thin material. We choose here a polyimide, and the pattern of the coil and the finger of interdigitated electrode is fabricated by gold. So it's nanometric layer. And the other part of the interdigitated electrode is fabricated by chrome and gold. Why chrome? Because the chrome have a particle mechanical property, is rigid under stretching. So when we make a cycle of this stretch, there is a crack induced in this metal, and this crack make the sensor very sensitive to strain. So if we look here to the variation of the resistance under strain for one nano layer of chrome and gold, we see how we have very important variation for very low strain with a George factor arrived to 6,657 which is very important sensitivity. So here we see one fabricated structure where it's fabricated by microfabrication technology. It's alternative technology to silicon method, where we use the photolithography technique and the liftoff and the wet etching. We see here in this image the finger of the interdigitated electrode with very low distance to around 10 micrometer and separated by around 10 micrometer or 12 micrometer. And here we see the crack on the edge electrode. So we succeeded to fabricate a durable, flexible, and thin materials that can wireless sensors that can be integrated in any type of structure. So now the next step is working to communicate with this sensor by following the resonance frequency of this tag. So thank you for your attention.
Vasilis, I see you have a question. Go ahead.
Thank you. Very, very nice presentation and very nice idea. How thick is your substrate, and do you plan to integrate them within the laminate, or to place it on the surface of the structure?
First, the thickness is controllable. So now we use 15 micrometer, but we can go less than that. It's dependent of the thickness of the substrate that we use. So it's very controllable. So no problem with the thickness. We can go to 10 micrometer or less than that. For the integration, sure, the idea is to integrate it or embed it on the structure, because if we want to put it on the surface, normally we can put a normal George factor without any George sensor without any problem. So the idea is to use it for application to embed it on structure, inside the structure.
Can you print it on a prepreg?
Sorry?
Can you print it on a prepreg?
Yeah, normally we can. It's microfabrication method. Normally, it's this fabrication method is known for silicon material, so for rigid material. So now we start to. I'm working to develop it to use it on flexible material. Normally. Because we arrive to integrate or to print this LRC component on flexible material, so we can do it on different type of material.
Thank you very much.
Okay,